Hi guys, so in the other video we learned how to prove that a limit in 3D does not exist. Today we're going to be doing something a little bit more difficult, and that is proving that the limit actually does exist and finding out what the limit is. So actually there are lots of ways to do this. I'm going to teach you 3, and these have all worked for me for all of the questions that I've ever done, so hopefully they'll be useful for you as well. So let's start with an easy example. So how would we go about finding what this approaches as it approaches 0? Well, if you've seen the other video, you might take a guess that you're going to try plugging in lots of numbers, and if they all approach the same limit, then it obviously exists. Well, you're never going to be able to plug everything in unless you're a computer, so you're probably going to try plugging in y equals 0, x equals 0, you're going to find that you're going to keep getting 0 over here. But then you can do x, any slope times x, any slope times x squared, x cubed, the list goes on. So you're not going to use that method. We're going to use something different. In this case, it's easy. This is a continuous function. I hope you can see that. So how about we just try plugging in x equals 0, y equals 0, and we're going to see what happens. Well, we're obviously going to get 0 squared plus 0 squared over 2, which is 0. So that's easy, and we can do that. The problem is that sometimes we get 0 over 0, and in that case, we're going to have to find another method. But always, if you can do this, if you can plug in 0, and that usually happens when there's addition in the numerator and the denominator has something else besides two numbers multiplied by each other, you're probably going to be able to, in those cases, just plug the numbers in, any number that it's approaching. Let's try something a little bit more tricky. So this is obviously, it looks a little bit more difficult than that case. What would happen if we just plugged in 0, 0? Well, in the denominator we see that there's only an x squared and a y squared, so if we plug in 0 for both of them, we're going to get 0 plus 0. And over here we're still going to get 1 minus 1, 0 over 0, an indeterminate form. So how about we try something different? You can see probably, if you remember how to rationalize the numerator or denominator, you're going to multiply the top or the bottom by the conjugate. This same thing, anything under the radical stays the same, and then you change this sign over here. And then obviously if you're multiplying by this, you also have to divide by this, because anything over itself is just 1, and you can multiply things by 1. It's not going to change the value. If you're wondering why I'm doing this even, what we're trying to do is change the form of this a little bit, and see if we can cancel things out, cancel in the denominator, and make this into a form maybe that makes it easier to substitute 0 and 0 in to get something that doesn't equal 0 over 0, or maybe we'll just get a number if we keep changing the form up. So if you ever see something with a square root, this is probably what the question wants you to do. So let's see what happens. So we have x squared plus y squared, we don't have these ones anymore, and we have an x squared plus y squared over here. We can cancel these out, and we're left with 1 over this big mess. Well, now, let me just write that out one more time. Yeah, square root of x squared plus y squared plus 1, and we have a plus 1 at the end too. Now, in this form, let's try plugging in 0, 0 again. 0 plus 0 over here, we still have the square root of 1 plus 1. Well, that's something that we can do. We're not getting a 0 over 0. We're not getting any indeterminate form. This equals 1 over square root of 1 plus 1. Remember, we're just substituting in the zeros. And that's actually square root of 1 is 1, so this actually equals 1 over 2. So look at that. All we did is simplify this. We just simplified the expression, and we got something, we just got a number spit out of that. We simplified it into something that would let us substitute in 0, 0, and we got the limit. So the limit of this function as it approaches the origin, 0, 0, is actually just 1 over 2. That was pretty easy, eh? Now we're going to try one last example. And this one probably has the most thinking behind it. These ones were kind of simple. Just substitute in the numbers, simplify then substitute in the numbers. This one's a little bit trickier. Okay, so I'll always try this one first. Try the easy one first, see if it works. If we do substitute in 0 and 0 for x and y, we're going to get 0 times 0 over 0 plus 0. 0 over 0, that doesn't work. How about this one? Can we simplify this? Well, let's try that. We'll see what happens. Okay, so this didn't really help us at all. This will be 0 plus 0, or 0 over 0 plus infinity. Yeah, that's just a big mess. That's not what we're going to do. We're going to use something called the squeeze theorem, and this sounds pretty intimidating, but don't worry, it's not. If you've already done the comparison tests, then this will come easily for you. So we're going to look at this function. Okay, we're going to approach 0 from the positive direction. So the positive direction obviously looks different in 3D, but just bear with me. So we're going to look at it in the positive direction. So whenever it's over 0, over or equal to 0, because obviously we're looking at the limit as it approaches 0. So we're going to let it equal 0 of this function. And we're going to try to squeeze it between something easier. So we're going to find a function that's less than, or sorry, not less than this one, more than this one, and that's always more than this one. Well, what we can tell, what I can see right away, what pops out at me, is that we have an x to the power of 4 in the numerator and in the denominator. Well, x to the power of 4, say it was just x to the power of 4 in the denominator. Let's just do a side note. Say it was just x to the power of 4, y to the power of 5 over x to the power of 4. Well, x to the 4 over x to the 4 is 1, right? Well, in the positives, that's just what we're looking at, remember. We're going through the positive direction towards 0. This number is always going to be more than x to the power of 4, because it's plus something. So if this was 0, it could be x to the 4. If this was 1, it could be x to the 4 plus 2. So this is always going to be bigger than just this x to the power of 4. So it's going to be a fraction that's, well, 1 or less than 1. So actually, this is just going to be making this y either the same or smaller. Hope I'm not just confusing you here. Hopefully you can just see this number is always going to make y to the power of 5 the same or less. So this is actually less than or equal to y to the power of 5, always. What's cool about this, okay, we have it squeezed between two easy things. What about if we take the limit of all of these things as they approach 0? So 0 is going to stay 0. The limit of any number as it approaches any number is just going to be that number. This, we don't know what it is. That's what we're trying to figure out. That's the same thing that we have here. And what about this one? What does it approach as we get closer to 0? Well, this is one of those things where we can just substitute it in. It's one of these easy ones. We can just substitute in 0, no problem. Even if there's no x, we can just substitute in y equals 0. So it is just going to be 0. This is an easy limit. Well, so now we have the limit of this function. It's greater or equal to 0, and it's also less than or equal to 0. How can that happen? Well, instead of being less than this one, instead of being greater than this one, we have the second option. It equals this one. That's the only option. You can't have something less than 0 and greater than 0. It has to be equal to 0. So just like that, by squeezing it in between two numbers and making them both equal 0, we know that this limit has to also be equal to 0. Limit, I don't really want to write everything out again, limit equals 0.